11.11 is on page 814. Talks about applications of Taylor polynomials. Now in upper division math, you get to use this. And normally you don't want the infinite. You want a certain number of terms, and they're normally denoted by T sub n. In every approximation that you give, you could figure out the error in your approximation. Now, I'm going to do an example, then come back and elaborate on how this works and tell you where everything is. One thing just I need to point out right now, if you want to figure out an n-Taylor approximation of a function, the remainder in using that n, you need an extra derivative. So if I'm doing 3, I'll find 4 derivatives. I'm doing a 4th degree polynomial, I'll find derivatives. So I'll point that out as we go on. So if I apply it to this problem, and this is on page 820. Approximate f by a Taylor polynomial with a given degree. Use Taylor inequality to estimate the accuracy in the approximation. And I'll talk about what that means. So here, you want to approximate x to the negative 1/2, which is 1 over radical x. A equal 4 and n equal 2, which means you need a 2nd degree polynomial. That's it. So you want to represent 1 over x squared, right, by roughly a 2nd degree polynomial centered at 4. So I would say 1 over x squared, not x squared, radical x, same thing, right? Who's counting, right? So 1 over radical x, I'm going to say that is f of 4 plus f prime of 4 times x minus 4 to the 1 over 1 factorial plus f double prime of 4 x minus 4 squared over 2 factorial. Basically, I'm done. That's all I need. Well, I'm going to put this on the side really quick. And I'm going to come here and say, well, alright, let's see how that works. Okay. It doesn't move. We could fix that. So if I say f equal x to the negative 1/2 evaluated at x equal 4, this is 1 over the square root of 4, that's 1/2. And if I take the derivative, that's negative 1/2 x to the negative 3/2, that's negative 1 over twice the square root of 4 cubed. That is, at 2 cubed, that's 8, that's 16. And one more. If I take a 2nd derivative, because that's all I need, that is 1/2 times 3/2 times x to the negative 5/2. So if I take 3 over 2 times 2 is 4, the square root of 4 to the 5th, that's 32 right there, times 4, 128, that's 3 over 128. Here you really don't need to worry about pattern because you only need 4 of them. So you're going to say that's 1/2 plus, that is negative 1 over 16 into x minus 4 to the 1 plus 3 over 128 times x minus 4 squared over 2 factorial. So you're going to say 1 over radical x around 4 is roughly 1/2 minus 1 over 16 into x minus 4 plus 3 over 256 x minus 4 squared. Now, in this class, you learn how to find those. You really don't use them, right? You're just learning how to do all of these things, but we're not really showing why do you use them for, but that's okay. The hard part is finding them. Now, like I mentioned, if they say find the 2nd degree, notice in part B, if I want to find the remainder in using the 2nd degree polynomial in absolute value that's less than or equal, m is a problem. Well, n, that is really 2 plus 1. That's very easy to find. And absolute value of x minus 1, I'm going to show you a nice trick. if you take 3.5, couple of ways you could do this really, and I'm going to show you both ways. One way is for you to say, you know what, I'm going to center this at 4, which means I'm going to subtract 4 from each side. And x minus 4 is going to be between negative 0.5 and 0.5, which means the absolute value of x minus 4 is less than or equal to 0.5. So you could just, so this is x minus 4, you could just say this is 3 factorial, this is 0.5, and then m is the problem. M is simply the next derivative in absolute value, biggest it could ever be. Another way of looking at this is that, wouldn't you say that this is decreasing? If it's decreasing, if you have a function that is decreasing, don't you always take the left endpoint and plug the actual 3.5 in? And 3.5 minus 5 in absolute value is 0.5. Regardless, doesn't matter what we use. Now, let's look at m. For me to figure m, I need to take one more derivative. If I take the third derivative, so every time I'm going to stop at some n, I take one more derivative for my, what do you call it? For my error. So that's 1 half times 3 halves times negative 5 halves x to the negative 7 halves. So wouldn't you say that this is actually negative 15 over 8, right? And the square root of x to the 7, I'm looking at a function, oh boy, forgive me. I'm looking at a function, isn't that always decreasing? If a function is decreasing, don't you always say that's the maximum it could ever be? So m is going to be the biggest this could ever be in absolute value, so that's going to be positive 15 over 8 times the square root of 3.5. You know what? I don't know why I'm writing so small. I have the whole page to go. So that is 3 factorial. This is going to be positive 15, always absolute value, 8 the square root of 3.5 to the 7th times 0.5. That's what the remainder is going to be, less than or equal. And you throw this in a calculator, and whatever that gives me, that turns out to be. So if you use the second degree polynomial to approximate 1 over square root of x, your answer is going to be accurate to 3 decimal places. And that's all you need. And here's another problem. Here I want t sub 3, so I could say t sub 3 is actually f of 1 plus f prime of 1, centered at 1, that is. Come on. Times x minus 1 to the 1 over 1 factorial plus f double prime at 1, x minus 1 squared over 2 factorial, and one more. So all what I need to do is find those. F is natural log of 1 plus 2x. If I play that at x equal 1, that's natural log of 3. If I take a derivative, isn't that 1 over 1 plus 2x times 2? If I throw a 1 in there, isn't that 2 over 3? But I'm going to say this is actually 2 into 1 plus 2x to the negative 1. If I take a second derivative, isn't that negative 2 into 1 plus 2x to the negative 2 times 2? Negative 2 into, I'm taking the derivative of this, 1 plus 2x to the negative 2 times 2. And when I throw a 1 in there, what am I going to get? In this case, I'm going to get a negative 4 over 3. Negative 4 over 3 squared, which is 9. And I need one more derivative. the third derivative is going to be a negative 4 times a negative 2 into 1 plus 2x to the negative 3 times 2. That's going to be, what is that now? 2 times 2 times, that's positive 16 over 3 cubed, which is 27, if I'm not mistaken. 2 times 2 is 4 times 2, oh, that's 8, that's 8, that's not 16, sorry. Very hard to redo those. So that's 8. And I'm going to take one more derivative just for the remainder. The fourth derivative is going to be, so this was 8, positive 8, so that's going to be 8 times negative 3 into 1 plus 2x to the negative 4 times 2, right? And let me get this out of the way. F of 1 natural log of 3 plus 2/3 into x minus 1 to the 1 over 1 factorial minus 4 over 9 times x minus 1 squared over 2 factorial plus 8 over 27 x minus 1 cubed over 3 factorial. That's going to be natural log of 3 plus 2/3 x minus 1 minus 2/9 x minus 1 squared plus 3 times 2 times 1, that divides that 4 times. That is 4 over 3 times 81 into x minus 1 cubed. There it is. And the remainder, if I want to find r sub 3 in absolute value, that's less than or equal to n plus 1, that's 4 factorial. And if I take this and I subtract a 1 from each, I'll get a negative 0.5 is less than or equal to s less than or equal to 0.5, oops, minus 1 of course. And that means absolute value of x minus 1 is less than or equal to 0.5, so 0.5 will be right there. The only thing left is m, and isn't this right here? What is that? Negative, that is 24 times 2, 48 over 1 plus 2x to the 4th. Isn't that a decreasing function? And if I'm looking at an interval between 0.5 and 1.5, and I have a function that's decreasing, always decreasing, wouldn't you say that left endpoint would be the highest? Isn't that 48 divided by 1 plus 2 times 0.5 is actually 1 all to the 4th power, right? And that would be my actual answer. This was to the 4th. Did I raise the other one to a power? Let me make sure I didn't mess up, because you raised that to the n plus 1. Yep, I messed up right there. Here we stopped at 2, so this is cubed. That's really my answer. I worked this out with those in. So this is to the 4th. And this turns out to be, in this case, the remainder is less than or equal to 0.0125. 0.0125. On a test, you really don't have to figure that out. You can just leave it like that out of mind. On the next example, well, we know this is going to be f of pi over 6 plus f prime of pi over 6 times x minus pi over 6. So I listed those out. I took derivative of sinus cosine. That's really easy to follow. Evaluated by pi over 6. I'm getting this to be 1/2 plus radical 3 over 2 times x minus pi over 6 to the 1 over 1 factorial minus 1/2 x minus pi over 6 squared over 2 factorial plus that minus radical 3 over 2 into x minus pi over 6 cubed over 3 factorial plus 1/2 into x minus pi over 6 to the 4 over 4 factorial. Now for the remainder, here it is. I'm going to write it out. So the denominator is 5 factorial. And on the interval between 0 and pi over 3 cosine, the biggest it could ever be is 1. We know that. And if I take 0 and subtract the pi over 6 from it, and do that to each I'm going to do. So if I do the traditional work, I'll get this to be less than pi 6, and I plug those in, and that